Neither. I was doing 3.6, and then I was like, we can't have that much. We do. But yeah, I did 3.2, and I mostly know what I'm doing. Yeah, I did one problem in 3.3.
So I started the test corrections pretty late last night because my idea was I only missed number 3, so I can just do the same thing I did on my paper. But then I was looking, and you had to do it in a way, like the way he said on this paper. And I was like, oh, now I gotta redo everything.
Yeah.
So I spent a couple hours on this. And I got the same answer, but I'm assuming I probably messed up.
Yeah, it's all and I have British stuff that I can read before. But it's not good till.
A lot of you. Property. For in the page. It's operate. So the expectation. So couple of page brackets here. So I'll solve it here. Yeah. I was thinking that you had done several of the things that we did. No, it was not.
So now at the main campus, we got posters advertising Costa Rica trip to plaster all over the early college. Because people don't know there's an early Costa Rica trip to the college. And I hear them asking to
Are they still accept people?
As far as I know, they just announced it recently. So I don't know if they're gonna get enough people in time though. I'm gonna go plaster all over.
We're still. Who knows?
Good.
Maybe we'll get Ireland next year.
Very lovely.
I'll commit to going to Ireland next year. In
Fire.
I think the food is gonna be good if
Tell them
you
that
travel
and it's
outside
sold.
of the United States, but it was really.
If you tell them that. He's looking pretty. He's got some weird things that he wants to see. So. Well.
Or you could just go on 2 study abroad trips. That's fun too. Yeah. I had a question. Shoot.
I talked about you with Dale.
Maybe.
I know it was.
I'm gonna assume that.
I want the way it sounds, the early
Okay.
or if I knew,
We need to
I
talk
want
to
to make
Allison
sure.
about that. Go by her office and talk to her about it today.
I have an advising appointment on November 3rd.
Just go by today.
Right.
Try to explain it to her.
Yeah.
Like, I mean, if I really need to retake one when I get to state, I can, but I kind of want to go ahead and get the knowledge. If I did okay in this class, I think I'd be pretty good. I just really don't want to make a B in this class. Hey, Brittany.
Where's
What? I don't know how to be in this class. Almost. Which one? Okay.
Right here. Why is circle exponent? The derivative of 2x to the third should be 6x to the second.
I think.
It's the same thing.
Okay.
What? I did all that work.
Well,
wrong with my exponent?
I don't know.
So,
No, just you get that one right.
No, I forgot. Three
What did you
instead.
get for your exponent?
I'll say, I was okay.
Plus four. This
I'll
must
look.
be-
I got some. Since you go.
Because this is the same as x to the negative one, and then if you switch it, and if you change it to put it in an exponent form, then you can use the power rule and it'll get negative x.
It's something like that.
There you go. I actually didn't do the chain for this one.
Oh, I see. So you
To do the derivative of e to anything, it's just e to the derivative. And this one, our exponent is actually its own function, so you have to take the derivative of the exponent as well. So that's just 4, so multiply e to x times 4. And then it's tangent of 3x squared because that's your second term if you're doing the product rule, you just leave it alone. Then,
Oh wait, wouldn't you have to take the derivative of the tangent, which is secant?
I did.
and then you do secant squared of 3x squared, and then the derivative of the inside, which is 16.
You got 1c.
No, but Josh did.
Yeah, I didn't get 1c either.
I mean, I got the 8 for the slope, but I never got the equation.
I got the equation 6x minus 8.
I just got an 8.
We both got it wrong though.
Well, in the same way, so at least we both weren't totally crazy.
That's what I'm saying. I didn't have that. How you do that? No, we didn't have to do it.
Did you already correct your 1 point or 1c?
Yeah.
How in the world did you know everything with a slope of -2? I don't have time to test every single point though. Obviously, that equation.
Okay, so you said it equal to -2.
That was so much simpler than I thought it was. I mean, I can't test
But
every
you
single
don't
point.
set f of x, you set f prime of x because the derivative is the tangent.
That's 6 out of 10.
Take my first. Oh, yeah.
On what, number 7?
On like all of them.
I actually got number 7 right.
I don't know what I did. I left like the bottom of the exponent on the thing.
It's just like, it doesn't count, just don't put it.
Yeah.
I think that's what you did for me for number, whichever one was the tangent.
Yeah.
No, never mind, I got 0 points for that.
Did you get 6 or 8? I missed all the derivative
I
ones
got-
on the right or the left side of the page.
I got 6, I got half of 8, I just, power rule and then.
Okay, so I got. I already messed up. Okay then. So. Why? I forgot about the natural log of n for the base, and I just did the change. That's what things went terribly wrong. Remember this one.
There you go, it should be this.
I got 4 seconds at the beginning.
No, that's right.
That is
Well,
right.
no, it's supposed to be 3 secant cubed. Once you multiply this, it'll be, okay, so what I did was I multiplied this 4 and this 3 to get 12. And then 12 squared to 4x times secant squared to 4x times 3. Just times it.
Actually, a 3 out and I left it like that and brought the 3 all the way. I'm on top of things.
So far.
Oh, man.
Amanda,
Yes.
for the rework test that they're going turning in, I just need the rework. I don't need the original.
Okay.
I'm just going to grade it as if I haven't seen anything before. Just give them the better of 2 grades.
Oh, wow. Good.
Okay. Make sure your name's on all the pages.
Yes, yeah, sure.
You have the original one?
He's in there.
Okay.
So we have a test next Tuesday then.
Yep.
It's
Yep.
not fair, we just finished the corrections on Monday.
That's right. Oh, dude, that's a cool sweater.
He's working on some tests in this class, whether it's corrections on one or taking another.
Yeah. Oh, wow.
How many tests?
Okay, so what we need to do today is
Pretty sure.
look at the part of the graphing analysis that we haven't yet, which is the show distance. So we need to examine that some. Have to look at vertical asymptotes and horizontal asymptotes or oblique asymptotes. So what I think I'll do is take an example to work with here and see what we'll get. Maybe do a couple examples with it. One X.
I'm gonna turn like this Frankenstein of a rough draft.
It's okay.
Final lesson.
It's okay.
X squared over X minus 1 squared.
Is it the way I had this one?
Over here.
Hey, Brittany, do you have a sheet of paper that I could use?
So what we'll do, we'll just do this problem. We'll go ahead and go through the whole thing, and when we get that way, we'll do the whole problem, but we'll also include the asymptote business of it as well. So just as another practice of doing the whole process one time. I think this see, might get messy when we get into the derivatives, but it's got all more into that. Okay, so the first thing we have to figure out the recollection. If you go in the order on that note sheet I gave, now you don't have to go in order, but have intercept, right? How do we find intercepts? Yeah. My intercept is easy. 0, up to 0. If that exists, which it does this time, it's 0 over 1, which is 0, so 0, 0. And then the x-intercept is solve that equal to 0. So x squared over x minus 1 squared implies you're only going to get x equal to 0 here, so my only x-intercept is y-intercept. Now we have to, this time we have asymptotes we need to talk about. So we'll talk about vertical asymptote first. So algebra, you should be able to recognize where there is located a vertical asymptote based on my inspection. But what do you really look for when you're looking for a vertical asymptote? What are you looking for in a function? Yeah, you don't want the denominator to be 0, so which x values cause the denominator to be 0 will be x values are going to be eliminated from the domain and will become a vertical asymptote. So vertical asymptotes really are just basically a domain issue. And so we would not want x equal to 1 because that would cause a 0 in the denominator. So have a vertical asymptote x equals 1. That's an equation of a line at x equals 1 is our vertical asymptote. But now, how does it behave at that asymptote? My question is, it's an asymptote, so it's going to get close in some kind of infinite fashion, but is it both sides going up to positive infinity, or both sides going to negative infinity, or some kind of opposite directions? And we achieve that by looking at limit as x gets close to 1. So look at limit x approaches 1 from the left of the function. And then we look at the limit x approaches 1 from the right of the function. That will tell me the behavior on either side of the asymptote will help me graph it. So when x gets close to 1 from the right, when x gets close to 1 from the left, on the left, so you're close to 1, but just smaller than 1. And if you square it, you're still going to be close to 1, a little bit smaller than 1, but you're going to be essentially close to 1 from the left side. And if x gets close to 1 from the left side and you subtract 1, so you're taking a number smaller than 1, subtracting 1 from it, now you're close to what number? And which side of 0? Negative side of 0, or squaring it.
Oh, no.
On both cases. So this becomes, again, close to 1 and close to 0 on the right-hand side, because we've squared it. We're making it from the right-hand side. So this is making it go to positive infinity.
Oh. So is the...
You approach 1 from the right-hand side. On this one, you're going to get a 1 from the right-hand side squared, and you're going to get a 0 from the right-hand side squared, And so you're going to get close to 1 over 0 from the right-hand side. So I'm dividing by very small numbers close to 0, but they're not equal to 0. But they're positive numbers, and so it's going to go to positivity on the right-hand side. So this particular function at the asymptote is going to both sides go up to positive infinity. This on that? Rizzo?
So is there no way to just see this visually by looking at the function? Are you just going to have to work it out with a limit?
What do you mean, look at the function?
Like, there's no indicators in the function that would tell you what direction it's going to take at the asymptote?
Well, not directly. I mean, from experience, I knew that squaring here is going to do something for me. But
Okay.
other than that, I'll be a little careful.
All right.
Okay, you need to show your limit work to show that you're examining the asymptote behavior. So I now know I have a vertical asymptote at x equals 1, and I know the behavior at that asymptote. Okay. Next up is horizontal or oblique asymptote. So we have either horizontal or oblique. Now, horizontal and oblique asymptotes, unlike over here, that was a domain issue. These are not domain issues. These are end behavior. So what's happening when I say end behavior? I mean, in particular, end behavior is x goes to plus or minus infinity. So I need to look out at very large x values using limits to determine what's going on with this function. So I'm going to look at the limit x goes to infinity and the limit x goes to negative infinity of the function x squared over x minus 1 squared. Okay, so I'm trying to do a limit x goes to infinity of x squared, excuse me, over x minus 1 squared.
Mm-hmm.
If I try to plug in using continuity theorem, you get infinity squared over 1 less than infinity squared, which is effectively infinity over infinity. Since this is infinity over infinity, then I can use L'Hopital on this one. That's going to give me 2x over, I have to do here a chain rule, so that's going to be 2 times x minus 1 times 1. I'll put that 1 up on the end. That's a chain rule. Don't forget your chain rule. Inside that parentheses has to be have a derivative as well for the chain rule. It happens to be 1 this time, so if you forgot it, you would still get the answer correct, but you might still get in trouble because, well, you didn't think about it. So.
Wow.
Now, if you try to plug in infinity in here, you get infinity over 2 times 1 less than infinity, which is still infinity, and so you get infinity over infinity. So we can apply L'Hopital one more time.
Mm-hmm.
We get 2 over, and then, let's see, we got a 2 there. And then times another 1 again for the chain rule. So this is just the limit x goes to infinity of 1, which is 1.
Nice.
Then if we look at going to negative infinity, we get the same, this will work out the same way. Question.
That 2 on the bottom is constant. Or is it?
Yeah, okay, so this is you get x minus 1 to the 1, so you bring down, it'd be like 2 times 1 times x minus 1 to the 0 times a chain rule 1, technically is what all the detail is in there. But something to the 0 power is 1, so that's just, so yeah, I have a constant multiple of 2 that I kind of held on to the side and then did the rest of it. Follow now? Okay. So that works out to be a 2, and then the 2's cancel to be a 1. And you'll see on this one, again, you'll get the same result. That's not always going to be the case, but this one you did get the same result, I believe. So if you plug in negative infinity, that's squared, it's going to be positive infinity, and then that's going to be squared, so it's going to be positive infinity. So you're going to have a L'Hopital again, and we already know what that's going to look like. 2x over 2 times x minus 1. And that's still L'Hopital. If you try a negative infinity in there, you're going to get negative infinity over negative infinity, which is still L'Hopital. So now we've got 2 over 2 again. So I get an answer of 1. So I get the right hand end behaves like the line y equals 1, and the left hand end behaves like the line y equals 1. So this tells me the right end asymptote is y equals 1. And this tells me the left end asymptote is y equals. So the graph will get close to the line, horizontal line, y equals 1 on both ends. It's not always going to be the same number. It can actually be different. Let's finish this. Well, we'll continue a little bit more, but then I want to do another one that's not horizontal. So I don't want to spend a lot of time getting into all the derivatives, but we'll keep working on it some. So we got some information. Let's try the derivative business now. F prime of x, just maybe that'd be good practice for us. So I'm up to step 3 now. We're looking at the first order stuff where I got to find the derivative. So what's the derivative of this function?
Are you going to use the quotient rule?
Yeah, you're going to use the quotient rule. That's why I'm a little hesitant to go too far on it, because it's going to take a while, but we'll start on it, at least to get you an idea. So quotient rule is going to be 2 times x minus 1 squared minus x squared times 2 times x minus 1 over x minus 1 to the 4th power. Maybe that's not too bad. Let's see. So I see an x minus 1 as a factor in a lot of places, so I could factor it out and cancel. So this one and one of those and one of those, that makes it 3.
Can you zoom in on that, please?
3?
Can you zoom in on that, please?
Yes. Is that better?
A little more. A little more?
Okay, all I did was I factored and canceled. Do you have to see all that, or do you understand?
I just wanted to know what exactly.
Let me show you. Let me do it another time. Let me do it a different way. I want you to really see what's happening, because I'm shortcutting, and that's I can see that's causing confusion already. Okay, so we're not going to shortcut. No more shortcuts.
I'm sorry.
But what I'm going to do, instead of shortcutting, I'm going to factor an x minus 1 out of the numerator. So I get an x minus 1 times 2x times x minus 1 minus, I have a 2 times x squared right there, so 2x squared. The denominator is still x minus 1 to the 4th power. So now this x minus 1 and one of these x minus 1s can divide out, and so I get f prime of x equals, and I can distribute this x minus 1 and one of those can be canceled. and I get 2x squared minus 2x squared is gone, and then I get a 2x over x minus 1. That wasn't too bad. Are we with us now on the algebra?
Where do you get 2x from?
I only did one little bit of calculus. The rest that's algebra, folks.
No, I'm sorry.
Okay, so now I gotta do what with this derivative function?
You gotta find the critical points.
Yes, how do I do that?
You gotta find where f prime of x is equal to 0 or does not exist.
Yes.
Is it negative 2x here?
Negative 2x. Good catch. Thank you. Yes, good catch, John. Everyone else catch that? 2x
Okay.
times negative 1 is actually negative 2x, not a positive 2x. Good catch.
Okay, what happened to get the negative 2x?
You just distribute that part.
Distribute which
We're
part?
going to set f prime of x equal to 0 or f prime of x equals does not exist. Okay, so equal to 0. The only way that's going to happen is if the numerator is equal to 0. So that means I'm going to have negative 2x equals 0 as long as x is not equal to 1. So that's going to give me x equals 0. Is a critical point. And then over here, does not exist. That means I'm going to have the denominator equal to 0. As long as the numerator is not 0, I guess. So this is going to be the cube root of 0, which is 0, so x is equal to 1.
Nice.
Now I need to do a analysis of the element. Move that a little higher. Move right up here, a little higher. Got a 0 and a 1 as my critical points. And then we have to find out sign changes. So how do we find sign changes?
You gotta plug stuff in.
Yeah, so what do we want to pick? How about
Negative 1? Come on, negative 1.
negative 1 works? Okay, negative 1, good. Negative 1 gives me a positive 2 and a negative 8, so that must be a negative sign.
Mm-hmm.
Number between 0 and 1 is maybe 1/2.
Yeah.
Half times negative 2 is negative 1. This will be a negative 1/2 cubed. That's negative. So I got negative over negative is positive. If we pick a positive 1 or bigger than positive 1, like say 2, then we get negative 4 over positive. So that's going to be negative.
Cool.
Also good.
Yeah.
From that, you should be able to identify local maximums and minimums. So do we have any local maximums or minimums? Have a local minimum at 0, comma f of 0, which is 0, 0.
Yeah, I get that.
How did you see that again? How did you look at this and tell that's local minimum?
So it starts off.
Negative means it's decreasing, and positive means it's increasing. So decrease and increase had to be a minimum. Now, is there a local maximum at x equals 1? And we went from positive, increasing, to negative, decreasing. Is there a local maximum?
Mm-hmm.
Okay.
No, because there's a domain issue of an asymptote involved. So that's not a local max.
What does that sign mean again? Does that mean it's positive and negative? Oh gosh.
You're with us on all of this?
Yes.
I need another board. Can I have one of my sliding boards back? You know, we used to have. I have to raise this board. Y'all got to copy down so you can tell me what we got. One intercept and we got up to 50 edits. I can copy that. Okay, good.
just gonna make it something.
Now what do we have to do?
So
I mean, I'm gonna make it.
Double prime of x. How do you find the second derivative?
You gotta take the derivative of the first derivative.
It's going to involve what?
Well,
Push.
hang on.
It's going to be negative 2 times x minus 1 cubed minus negative 2x times 3 times x minus 1 squared times 1 changing over x minus 1 to the 6th.
Got him.
It looks real messy, but a little bit of algebra will help clean this up. First of all, I see two big terms in the numerator. First term and then minus in the second term. In each term, I see an x minus 1. So there's a square factor and a cube factor. I'll factor out a square, so that's x minus 1 squared times, and then I got negative 2 times x minus 1. And here I'm going to have plus 2x, actually times 3 is 6x. 6x. And over x minus 1 to the 6th power. Again, I have, because I factored it, I have a factor divided by the same factor, so that can go with those. And I get, let's see, negative 2x to 6x, it's like 4x plus 2, right?
Yeah. That's it.
All right, okay, good. And then x minus 1 to the 4th power.
Mm-hmm.
So it wasn't as bad as I was afraid it was going to be.
It's just a portion.
Now what?
You gotta find the critical second order critical points.
So let's see, f double prime of x equals 0. The only way that happens is if the numerator is 0, so I want 4x plus 2 equals 0. So x equals to negative 1/2. I want does not exist. The way that happens is if the denominator is 0 when the numerator is not 0, so I want x minus 1 to the 4th equals 0, so x equals 1. So I get negative 1/2 and 1. And I gotta test those again. So let's see. I go left of negative 1/2 in this function. So negative 1. Okay, so that's negative 4 plus 2 is negative 2. This is something to the 4th power, which is going to be positive. So apparently that's negative. If I pick something between the two, 0 would be convenient. So how about 0? That gives me 2. Now positive, so that's positive. And then bigger than 1, how about 2? So what is that? That's 8. That's 10. That's positive divided by positive is positive.
Oh, sweet.
So now what can we observe from this chart? What do I see right here? Yeah, it's a local minimum on the derivative function, but that's not what I'm looking for on the original function. It's not called a local minimum. It's where the concavity changes, and we call that an inflection. An inflection point. At negative 1/2 F of negative 1, which is negative 1/2, what's that? What is that? X squared over x minus 1 squared. So 1/4 over negative 1/2 minus 1 is negative 3/2.
Mm-hmm.
4 over 9/4, is that right? So 1/9. Did I do that right?
No.
Negative 1/2 squared over negative 1/2 minus 1 squared.
Yeah.
That's 1/4. That's 3/2. Yeah. Yep, 1/9. Okay, good.
What is that?
It's fine.
1/9.
Now I got all the information I need. I got a sketch graph.
Yay. It's like drawing in math class.
We had one intercept at 0, 0.
I've already failed too, so it's okay.
What does that say? Config?
And a local minimum at 0, 0. This 0, 0 is also a minimum. We had no local maxes. We have an inflection point at negative 1/2 and 1/9.
One really
So I'll
dubious.
say that's about, I'm going to make a real broad scale on my x-axis. That right there is going to be my inflection. So this is negative 1/2 and 1/9 is an inflection point. What else did I have that I need to put on the graph? An asymptote or two. One of them was where?
X equals.
X equals 1, so that's going to be about right. That 1/2 scale is right, then I'm going to be out about here somewhere.
Oh, dang.
This is the line x equals 1. And then I also had a horizontal asymptote we saw right here, a billboard. The horizontal asymptote was 1 in both directions. So there's the line y equals 1.
Yay.
We just got to somehow connect the dots.
Mhm.
Oh, let's read the rest of it. We got more information. I apologize. More information.
Hang on.
From the first derivative way back over there, when we're left of 0, we're decreasing. So at this, from here to here, we're decreasing. Between 0 and 1, we are increasing. And after 1 and on, we're decreasing. So we saw that from the first derivative way back over there. And then we saw in the second derivative areas of concavity. So the left of negative 1/2, so from here this way, we're concave down. And then after 1/2, negative 1/2 up to 1, in this region, we're concave up. And we skip over the 1 because that's a domain missing place. And then over on the other side of it, it's up again. Now I should have all the information. I should be able to sketch it in. I know that the vertical asymptote, it goes to infinity on both sides. So my graph has to be something like that on both sides of that asymptote. I know that much so far. It has to, on the right end, it has to get close to the horizontal asymptote of 1. So, and it has to stay concave up. So it's got to be curving up the whole time. So I'm going to say it must look about like that.
Mm-hmm.
Now, folks, is it possible? This is just a question before I finish the graph and support a question. Can I, not on this function, but in general, is it possible to cross the horizontal asymptote
Yeah.
You can't cross the vertical asymptote because that's a domain issue. There's no point there. It's not a value. But I can cross a horizontal asymptote. In fact, I can cross it multiple times and still hone in on that horizontal asymptote.
No.
Why would I know I'm not crossing it on this one? This is important questions. Information that tells me is that I have to approach this asymptote from above it like that. I cannot do, over here first. On this asymptote, horizontal asymptote, I cannot do this. Let me make it more pronounced for you.
Vernal.
If I did that, if I did this and approached I'm hitting the horizontal asymptote as I should, getting close to it. Why is this graph not allowed on this function, even though it could be allowed on other functions and would actually be required on other functions? What up here tells me that this is not the right picture, that this is the right picture?
Does it have to do with concavity?
Because it's always concave up. This one's always concave up. This one is not. This one's concave up until it gets to about there. And then it's concave down. Y'all see this? That was this one changes from up down. And so if you go below the axis, you're going to be concave down approaching that asymptote. And so that's not going to be possible here. In other situations, it will be required. Okay, what other information I know? This has got to be increasing in here and concave up there, but a minimum right there. So it's concave up, a minimum. And then at that inflection point, it turns to concave down and is decreasing. So it's coming in from this asymptote, concave down.
Whoa. I did not see this coming.
I'm concave up, and then all of a sudden I turn to curving down so I can approach that asymptote. Once again, because this is always a decreasing function and concave down, it has to be like that. And so the only way to get close to the the horizontal asymptote, is to stay below it. If I'd gone above it and come back down to it, then I would have changed my concavity. I can't do that. So there's my picture of the function. One more real quick. I won't go through the whole thing, but I want to just do another one that has a different kind of asymptote called oblique. And then we'll just open up the general questions, and that'll be it. So we'll start over in here with horizontal and oblique and a different function real quick. First, any questions on the one we just did and drawing the graph? We did the whole process. It was a good little function to mess with. Any questions on that one? If you know, I want to do another example.
Thanks, man.
Okay, so let's try f of x equals x squared minus 4 over x plus
You gotta have it be top heavy. That's it. I remember this. It's oblique.
I'm not going to go through all the rest of the pieces of this puzzle. We've done that now 2 or 3 times. I think you should have that down. So let's practice one more time on the asymptote part of it, because we've only done that once. So let's start with, I'm not only doing horizontal oblique, I'm also doing vertical, but we'll do the vertical one more time here. So let's do vertical asymptote. How do we look at vertical asymptotes?
It's a
Domain issue. And where's there a domain problem with this one?
You could say -1.
X is -1. And then how do I decide what the behavior at that asymptote is? Yeah. Limit x approaches -1 from the left of x squared minus 4 over x plus 1. And the limit x approaches -1 from the right of x squared minus 4 over x plus 1. Am I writing? Where's my limit? Okay, so same type of thinking as before. I'm trying to approach -1 from the left, and I want to think through what that means in terms of result. So if I get close to -1 from the left, then this x is close to -1. I'm going to square it, which is going to leave it close to 1, not -1. And 1 minus 4 is close to -3. But now, if I get close to -1 from the left side and I add 1 to it, I'm close to 0, but which side of 0 am I close to? The left side, so 0 from the left side. Follow that thinking?
Mm-hmm.
If I'm on the left, you understand why it's the left side of 0? Because you're starting left of, next number line, you're left of -1, left of -1. You move over 1 unit, you're still left of 0. That means I'm dividing a constant by a very small, close to 0 number that's negative. That's going to come out to be positive infinity. If I approach -1 from the right and go through the same game, a -1 squared makes a 1, minus 4 is -3. But this time, when I approach -1 from the right, I'm on the right side of -1. If I take 1 step forward to the right, I'm going to be on the right-hand side of 0, which is going to come out to be a negative infinity. So now I know how this function is going to behave near the asymptote. The left side is going to infinity, and the right side is going to negative. Okay? What about the horizontal asymptote business? It's a little oblique.
It's end behavior.
Right?
Right? It's end behavior.
That's the end behavior, that's right. So vertical asymptote has to do with domain, issue. That's exactly right. And the horizontal or oblique.
Yeah, we're gonna get some obliques today.
Going to be in behavior issue. So since I'm talking in behavior, then I got to think about letting x go to infinity and negative infinity. So limit x goes to infinity of x squared minus 4 over x plus 1 is infinity over infinity. If you plug in an infinity, you get infinity divided by infinity. So I can use L'Hopital here. And I get 2x over 1, which is, if x goes to infinity, that's just infinity.
Oh, sweet.
And I think if you do the left-hand side, you're going to get the same type of thing, except for it's going to go to negative infinity. So x squared minus 4 over x plus 1 is infinity over negative infinity, which is still a, as Reza said, how did you put it?
The hospital?
Yeah, positive infinity over negative infinity. It's not truly infinity over infinity, so you call it a...
I called it a liberal interpretation of a...
Liberal interpretation, yes. Liberal interpretation of infinities. We get positive infinity over negative infinities, and so that's going to be still a L'Hopital. We're going to do limit x approaches infinity of 2x over 1. So x goes to negative infinity is going to give me a negative infinity. Okay, well, what does that mean?
Well...
So as I go out to the right end of things, I'm going up to infinity. When I go to the left end, I'm going down to negative infinity. But I need to check to see if there's an oblique asymptote. So this only looks for horizontal asymptote, and I don't have a horizontal asymptote. So this says, to me, no horizontal asymptote. it does not preclude an oblique asymptote.
Mm.
So to determine that, what we'll do is divide. We'll divide. So we'll take this function, and it's x squared minus 4 divided by x plus 1. So I'm just going to divide x plus 1 into x squared plus 0x minus 4.
Oh no.
Y'all remember this from algebra?
I remember this from...
Yeah, I hope I wouldn't have to see that again, but yeah, it's still there.
But no,
I don't like this.
I remember this.
I remember how to start this.
Yeah.
So we
same.
divide by saying x times what gives me x squared? That would be an x.
That's my X.
And so x times x gives me x squared, and x times 1 gives me an x. You subtract that, just like you do in division in 4th grade. And what do you got? Let's see, x goes 0 minus 1 is negative x. Bring down the next term. Well, what times x gives me a negative x? That must be a minus 1.
Mm-hmm.
Minus 1 times x gives me negative x. Minus 1 times 1 gives me a minus 1. Subtract that. And negative 4 plus 1 is negative 3. So what this tells me is that f of x, so what I've learned here, is that f of x, which was x squared minus 4 over x plus 1, can be rewritten as a quotient, x minus 1, plus the remainder divided by the divisor.
Oh,
We're doing that in algebra now?
yeah.
I've rewritten my function from a just a single quotient. So think of it in terms of numbers, going back to 4th grade, you've got an improper fraction here, folks, improper fraction. Now you've got a mixed number here, a whole number plus a fraction. So went from improper to mixed number form, just like in 4th grade. So what does that mean? If I look at the limits now, folks, look at the limits now. Consider x goes to plus or minus infinity.
Oh my gosh.
What do you observe? Let me move this arm so you can see that. Camera. What do we observe now on this new look of the same function, but just a different look? As x goes to plus or minus infinity, what do you observe here? Well, I'm looking at this view of the function. This stuff here goes to infinity like we saw before. But there's something more emphatic. This term out here on the end, this stuff still goes to infinity plus or minus infinity like we've seen before. That's fine. Plus or minus infinity. We can handle that. But what about this term right there? When x goes to plus or minus infinity, what happens to this term right there? It goes to 0.
Oh my gosh.
So what does that mean?
It's irrelevant.
That means when you go out to the ends of the graph, the original function here begins to behave like that function right there. Because out at the ends, this part of the function, this little bit of extra add-on part, effectively reduces to 0. So as x gets very large, this part effectively goes away, and the graph begins to behave like that function right there. Are we following this?
Oh my
So
gosh.
this function plus 0 is effectively the answer. So what all this tells me, if you look at this, I can now say I have an oblique asymptote. Is line y equals x minus 1. That's this stuff right here.
I'm impressed. That's cool.
So you could actually, in theory, folks, you could actually have other types of asymptotes. by this same thinking process. This one came out to be a linear equation with a slope of 1 and a y-intercept of -1 and all that. But I could have had, if I had a broader, bigger function, this could be a parabolic asymptote. So the ends of the graph would behave like a parabola, and the inside and the middle could be doing all kind of other things. So you can have more asymptotic behavior, but we'll only discuss horizontal asymptote or oblique asymptote. So if when you divide, if you divide this, and if this comes out to be a degree higher than 1, then you just say we don't have an asymptote. Are we following that?
So if we get the same limits up there, we horizontal, but if they're different, we go to oblique.
If you get a constant limit up here, if you get a constant limit like 1 or 7 or something, and they can even be different. You can have a 7 here and a 5 there. Okay. You can have a constant value as your limit up here. You have horizontal asymptotes.
So you're done with that part.
You're done. Just go with your thumb. Go on to the next thing. If these come out to be infinity, then you need to consider whether it's an oblique asymptote. And then that's when you do this game, you divide. If, when you divide, the quotient comes out to be a degree 1 function, then we will call it an oblique asymptote. If the quotient comes out to be, which is this part right here, if the quotient comes out to be degree 2 or higher, in theory, it could be considered another type of asymptote. We're just going to ignore it and say no asymptote. Okay? So you're only going to have 2 types considered, horizontal or oblique. Anything else, call it no asymptote. Now, everyone call that? Good question, Jim. So if you get constant values here, then you have a horizontal asymptote of some sort and you're done. If you get infinities here, then you need to check for oblique.
Mr. Gaddis,
Mr. President.
is a parabolic asymptote still called an oblique asymptote?
No, oblique would only be, good question, oblique is only if it's a line with a slope other than 0. So horizontal is a line with a slope of 0. Oblique is a slope of anything other than 0, other than vertical. Good question, no. Okay. Any other questions? Under 8 minutes, 8 minutes. Okay. Y'all want to try another one of these that are oblique just to make sure you can.
Oh yeah, I was gonna ask something.
Yes, please.
I want to see what this looks like when it's graphed.
Okay, so we'll try another one of these type, and we'll only look at the horizontal and oblique asymptote aspect of it. Again, the rest of the detail is still available. I mean, you still need to be able to do all the other stuff we've done, but we're just focusing on that one aspect right now. So let's make up another one that's going to work out that way. How about by the way, I guess I should have said, when you get ready to graph, let's go back over here for just a minute, I apologize. I'll understand that this is an asymptote that must be drawn on your graph.
Yeah.
So,
Yeah.
how do I do that? Okay, well, that's a good question. So we'll do that real quick. You know, whatever else is going on, you got vertical asymptotes, you got intercepts, you got max and mins. This asymptote right here is oblique, but okay, that's just the equation of a line. So how do you graph the equation of that line? Got a y-intercept of -1 and a slope of 1. So I go to -1 and I make a line. Slope like that. This is y equals x minus 1. And whatever else happens, my graph is going to be close to it at the ends. On this one, I also had a vertical asymptote at -1. So you would have some kind of vertical asymptote over here, x equals -1. It goes to positive infinity on the left side, positive infinity on the left side somehow, and negative infinity on the right side somehow. So whatever else happens, I mean, it's going to do something in here. This one might go up and come back down to the asymptote. I don't know. I haven't done the rest of the analysis. But somewhere out here, it's going to have to get close to that asymptote, and somewhere out here, it's going to get close to this asymptote. Whatever else happens in between. Okay? So back to here, we'll do ignore the vertical. That's fairly straightforward. Let's look at the horizontal and oblique. So I can limit x approaches infinity of this. I get like infinity over infinity type of gain again. So I'm going to do L'Hopital once again. And you'll see that it's still going to come out to be infinity in the end. You get a 2x minus 3 over 2. So x goes infinity, that's going to be infinity. And if you do negative infinity, you get the same idea. X squared minus 3x plus 5 over 2x plus 1. L'Hopital. Negative infinity, we're going to negative infinity this time. So that's 2x minus 3 over 2. And if you plug in negative infinity, you're going to get a negative infinity. Okay, so that information tells me that I do not have a horizontal asymptote. So not horizontal asymptote. It could be oblique, or it could be none. So to test that out and get the answer, we'll divide it. So let's see. 2x plus 1 into x squared minus 3x plus 5. So what times 2x gives me an x squared? 1/2 x. 1/2 x times 2x gives me an x squared, and 1/2 x times 1 gives me a 1/2 x. Subtract. -3 minus 1/2 is -7/2 x. Bring down the next term. What times 2x is going to give me -7/2 x? Yeah, -7/4. I think. I mean, you're asking, so what times 2 gives this? Well, 2 times 7/4 is going to give us 7/2, isn't it? So -7/2 x, and then -7/4 minus. And now we've got 5 plus 7/4, so that's 27/4.
I love it. Oh my gosh, and then you're going to have to divide that by 2x plus 1.
No, that's the remainder.
Yeah, the remainder, right? That's what it does.
Yeah.
The remainder is
So,
over the...
f of x, which was originally x squared minus 3x plus 5 over 2x plus 1, can be rewritten from improper fraction form to mixed number form as 1/2 x minus 7/4 plus 27/4 over 2x plus 1. That division, all it did is rewrite my function in a different form. improper rational to mixed number. But like before, when x goes out to infinity, when x gets very large right here, you're dividing by infinity into a constant number. So some constant number divided by infinity is effectively 0. So this, at the ends, this goes to 0 as x goes to plus minus infinity. So what it tells me is my function at the ends of the graph behaves like this. So I get an oblique asymptote at y equals 1/2 x minus 7. I can draw that oblique line on my graph along with whatever else I have, and remember that my graph has to get close to that line as x goes to infinity or negative infinity.
Mr. Gaddis,
Yes.
so
Yes.
what disqualifies an oblique asymptote?
What do you mean?
Like, when is there going to be no horizontal or oblique asymptote?
Good question. If you remember from a previous chapter, it might have been in the review chapter about precalculus. I can't remember exactly which chapter, but there was a theorem. That was a review of a theorem you did in precalculus that said if you've got a rational function, if the degree of the two, the numerator and denominator degree was the same, then the horizontal asymptote is at a over b.
Yeah.
If the numerator is less than the degree of the denominator, then the horizontal asymptote will be at 0. If the degree of the numerator is bigger than the degree of the denominator, they said there's no asymptote. We're saying if the degree of the numerator, is 1 more than the degree of the denominator, then you will have oblique asymptote. If the degree of the numerator is 2 degrees more or more than, if the degree of the numerator is at least 2 degrees bigger than the degree of the denominator, then we'll call it no asymptote.
Okay.
Careful. When is it a whole?
A whole?
Yeah.
Okay, a whole would occur when you have a factor in the numerator and denominator that can both be canceled simultaneously. That gives you a hole in the graph. If you can't cancel with the denominator, then it's an asymptote in the graph. They're both a domain issue, but if you can cancel it, then we can call it a hole rather than an asymptote. Answer your question, Rezo, about the distinguishing characteristics of the function?
Yes.
I have a question.
Yes, Chloe.
So building off that, if we see a function and the numerator has a degree that's 1 more than the denominator, do we
Yes.
know that it's going to be an oblique asymptote so we don't have to test for the horizontal one?
Yes. Since we've discussed that now, we'll call that a new theorem, an extension of that previous theorem. We'll call it that, or call it a lemma if you want. And we'll say that if you observe that and say, well, since the degree is 1 more than this one, then I have an oblique asymptote, and I'll just go straight to this step right here. And you can skip the testing horizontal. So yes, I'll grant that. Sure. Okay. Any other questions? I think we're about out of time. So any other questions, real quick? For Monday, you should try to finish up on the homework on section 3.2 and 3.3. And Monday will be a review day. We've covered all new material now. So Monday will be a review day, and Tuesday will be a test on this block of material. We covered 4 sections on this block. We covered sections 3.1, 3.2, 3.3, and 3.6.
Okay.
Test will be mostly, we'll have some protocol work to do on the test. Just straight up do some limits, but then you'll also have graphing questions like we've been discussing here where you all right, see y'all Monday.
It just blazes by.
So what am I going to talk to Ms. Holmes about right now?
The answers for all the different
Just about counting in general.
What,
Just after Ms. said to you.
like, what has Ms. After said to you, like, specifically, like, you can't take it?
I just heard that Ms. Hahn said they weren't paying for it.
So Absher hasn't actually said anything?
Yeah.
Well, now they're making it where they don't even seem to talk to them.
Yeah.
Yeah. They don't even want us doing this.
Doing this?
Well, they can't stop this.
True story.
What's done is done.
This train is gone.
Do you have answers on
On the last test,
Yeah.
I mean, I have what I got.
6.
I got that one.
I just need the answers. I'm gonna work with them later.
I didn't get that one.
Yeah, I just wanna write these down real quick.
Like, this is what I gotta get.
That's what I got. Let's see.
Yeah,
No.
compare to this.
And you do,
And you do logarithmic differentiation on that one.
Really?
you don't have.
You pretty much have to on
Oh,
number
work on
6.
Cause there's 6 ones. Cause it's 8.
Oh.
It's a whole big long.
Was it just for you or was it for all of us?
What, the thing about the thing from Kelly?
I mean, we've already seen them like twice already, so, and I do think that this.
And then I use it again. And we'll see what we got.
This one, I did logarithmic differentiation on, and I'm fairly certain that's the answer, but I'm not super sure. But I'm fairly certain.
That's good, really sure.
Yeah, really certain is.
So on this, you just missed the 1/2 here, I showed you.
I got you,
that.
Chloe.
I know, I was so
Text me if you
stupid
need
doing that the day of the quiz. I couldn't figure out what gives me just an X?
No.
I
I
just
know, on
looked
that
at
one-
it, looked at it, looked at it.
For some reason, I
This
thought
is
that,
just like 4 chain rules.
4 chain.
Yeah.
4 chain.
And hopefully I haven't made
Entire,
any
like,
algebraic things, but I think that was over.
Do you do this when you take the test also?
do you finish
It
it in
depends
the
on-
time?
It
that we
depends
take
on
the
if I
test?
have things to grade or not.
I was like, this is crazy.
Yeah, I'm impressed. 17. I could probably just find this.
Yeah, that one is like straight out of the, it's either the book or the,
This one we did in class.
yeah, that
this
one
one's
is-
in the book.
Sweet.
yeah.
I got,
Thank
the
you,
one we did in
Sonia.
class.
I'm just gonna
It's
go
in
for it.
the book.
I'm done.
Thank you, Ms. Klinger.
Thank you.
I still don't think that's
You don't think derivatives were easier than
Well,
limits? I always thought
I
derivatives
feel like they were easier, but it's taken me until now for them to feel like really easy. Like I can do derivatives
Like if you could
really
do
well
last
in
test
my
now,
head.
then you would be.
Oh my
okay.
goodness, yeah, I would be totally okay if I could do last test today. But we didn't do it today, we did it a week ago, so